Hello, everyone. So first, I want to thank the organizers for giving me the opportunity to present here. I am Sumit Tarafder. I am a graduate student at Virginia Tech, and I am going to present today our work, lociPARSE, a deep learning-based method for scoring RNA 3D structures. Now, I want to give a brief description and motivation why we need to develop such a scoring method for RNA, especially RNA. So RNAs have gained a lot of attention in the recent times, especially since the COVID-19 pandemic time, which has shown us how RNA was actually the reason for both the problem and the prevention. But also, apart from their RNA-targeted therapeutics and their effectiveness, we are seeing a growing number of scientific studies every day that shows us how RNA, especially some long non-coding RNAs, can actually play crucial roles in our many cellular and genomic activities. So that means clearly accurate identification and accurate prediction of RNA 3D structures are going to be very important in the structural bioinformatics in the upcoming days. But if we look at the current state of the RNA 3D structure prediction using deep learning, so this is the figure 1 taken from AlphaFold 3. I forgot to put the label. So if we concentrate on the RNA structure prediction, the nucleic acid part, based on the Cas15 data set, so you can see that the success rate of AlphaFold 3 on RNA structure prediction is barely 40%. And if you compare that with the protein monomeric structure prediction on the far right-hand side, you can see that the structure prediction accuracy is like more than 82%. So basically more than double. So this means two things, that there is a major room for improvement in terms of RNA structure prediction using deep learning, which is a completely different topic. But most importantly, it means that since the current state of the art is not that stable in terms of prediction, so some of the structures will be good and some of the structures may be not that good. So this is where a scoring method for RNA actually might be helpful in RNA structural research. So for example, suppose you are working on your own research study with RNA sequences, and you have an ensemble of RNA 3D structures like this for a given particular RNA sequence. Now these ensemble, these RNA 3D structures may come from many different RNA structure predictors or sampling methods. Now the question is, can you actually identify which one is actually the best structure out of this ensemble? Well, if you have the ground truth or experimental native structure present to you for that particular RNA sequence, what you can do is you can compare each of these structures with the ground truth, and you can easily know which one is actually the best structure. But what if the RNA sequence that you are working on is actually a novel RNA sequence, and you do not have the experimental structure available to you in the protein data bank? Well, what will you do in that case? Well, you can use a scoring method such as, or quality assessment methods such as lociPARSE, and it will be able to predict the structural quality of each of these structures in the absence of ground truth. And eventually what you can do is you can pick the structure with the best predicted quality and use it in your subsequent experimental design. So basically, that was the reason or motivation behind the development of this method, lociPARSE, which is now published in Journal of Chemical Information and Modeling. So two things about lociPARSE. One is architecture is invariant. That means no matter for a given RNA 3D structure, no matter how you rotate the molecule or translate the molecule in the 3D space, the output probability will be obviously same. So that's invariant property. And the second thing about lociPARSE, which makes it a little bit or different than most other state-of-the-art methods in the literature, is that lociPARSE can accurately predict per nucleotide quality also. So that means for a given structure, lociPARSE will be able to identify which part of the structure is accurately predicted and which other parts are actually poorly designed. So, and obviously, if you have all these nucleotide level scores, you can take an average of them and you can get a per molecular level score or a single molecular level score. So these will be the two outputs of our method, lociPARSE. So to develop such a deep learning-based method, the first question that we asked ourselves is, what should be the target metric, or what should be the true training levels for the method to train on? Popular choice in the literature is RMSD, or root mean square deviation. But as we know, that RMSD is a superposition-based metric, and superposition between two structures, let's say a native structure and a model structure, itself is an optimization problem because it can be affected by the outlier regions in the structure. So that's one problem of RMSD. And the second problem is, trivially, RMSD is not assessed per nucleotide. But for our method to train, we need per nucleotide level scores, which RMSD will not actually be able to give us trivially. So for these reasons, we have chosen to avoid work. Instead, we have targeted a different metric called LDDT. LDDT's full form is local distance difference test is always a value between 0 to 1, and it's a completely superposition-free metric. Now, you may have heard about LDDT before, but briefly, this is how LDDT computation works between a native structure and a model structure. So first, what LDDT does is, for each atom present in the structure, it will define a 15 angstrom radius to find out the neighboring atom pairs, and it will calculate the distances between all these atom pairs in the native structure. Then, for the model structure to evaluate, LDDT will again compute the distances between the same atom pairs, and then it will find out the deltas or the distance differences between the atom pairs. These distance differences will be then evaluated against 4 separate error thresholds, 0.5 to up to 4 angstrom, to see actually how the errors compare. And these final evaluation will be actually contributing to the final LDDT calculation. So basically, this is how LDDT works. And as you can see, the way the LDDT computation works, it can give us those per nucleotide scores, which we can then take and train our deep learning-based method. So now that we have calculated the LDDTs from using the software OpenStructure. So now that we know how LDDT works, now I will actually explain the basic workflow of our lociPARSE architecture. That is how it takes the RNA structure as input, and it can predict the individual qualities per nucleotide. So for a given RNA 3D structure, what lociPARSE first does is it calculates the frame representations for each of those nucleotides. Now, this frame is calculated from the P, C4 prime, and N atomic coordinates. Now, what is a frame? A frame is nothing but a set of 3 orthogonal unit vectors, which actually gives the sense of the orientation of each of those nucleotides in the 3D space. And also, for each nucleotide, we'll generate nucleotide sequence features and nucleotide pair features, but the pair of each nucleotide will be actually defined by the k nearest neighborhood. So all these features and the per nucleotide frames will go as input to our main invariant point attention block. Now, the invariant point attention, or IPA block, is actually inspired by AlphaFold 2, but here it is modified to make it locality aware. So what does it mean by locality aware? That is, during the calculation of the attention per nucleotide, rather than paying attention to all the other nucleotides in the sequence, what each nucleotide will do is it will only pay attention to its neighborhood nucleotides, which is defined by the parameter k. So that's why you can see that all the internal components of our attention calculation blocks, it has the dimension of L cross k rather than L cross L, where L is the total number of nucleotides. So these sparse attention calculation technique is because of 2 things. One, it actually speeds up the calculation process. And the second thing is this locality-aware architecture actually resembles the way that we are trying to learn, that is the LDDT, which is also a locality-aware metric. So this brings the synchronization between the architecture and the training levels that we are trying to predict. And finally, these per nucleotide attention probabilities will be converted to per nucleotide attentions will be converted to per nucleotide probabilities using a feed-forward network layer. And then all those nucleotides probabilities will be actually averaged to get 1 molecular level score. So these will be the 2 outputs of our architecture. And the entire pipeline is available as a software to use in this GitHub link. So if you want to use, you can easily install and use it. So in terms of the features, we have used absolutely primitive level features. So for nucleotide, we have used simple one-hot encoding and positional level encoding of the nucleotides. And importantly, for the pairwise features, for each pair ij of nucleotides, we have used sequence separation I minus j. And importantly, the distances between the P, C4 prime, and N atoms of the ith and jth nucleotide. Now, instead of using raw distances, what we have done is we have used Gaussian radial basis functions, so that because the distances can have a long range, so it might be difficult for the neural networks to understand and find patterns. So using Gaussian radial basis function, it actually smooths the landscape and makes it easier for the network to find some patterns and learn it. And to train and test our deep learning-based architecture, we have collected the sequence set from the published work of TR Rosetta RNA, which contains sequences released before January 2022. So what we did is, for each sequence present in the dataset, we have generated many deep learning-based and non-deep learning-based methods structure. So in total, we have more than 50,000 RNA 3D structures in our training set, containing 2 million nucleotides. And for testing our method, we have used basically the Cas15 dataset. So all the submitted models in the Cas15 dataset. So in total 12 targets and 660 structures. And so just to mention that the Cas15 happened on May 2022. So this makes the training set and the testing set completely non-redundant, at least in terms of sequence and in terms of time. And in terms of for evaluation, we have compared our method against 6 other state-of-the-art methods. 4 of them are energy-based, calculation-free energy or non-deep learning. And the 2 other methods are deep learning-based methods, ARIS and RNA-3D-CNN. And to mention here, the 2 deep learning-based methods actually use RMSD instead of LDDT to train their method, which is completely different than ours. And to understand the performance, we have used these evaluation metrics, mainly the correlation coefficients, Pearson, Spearman, and Kendall-Stowe, to see how the predicted quality scores actually correlate to the actual ground truth LDDT scores. So that's where the correlation coefficients will come. And we have also calculated the diff, which is an absolute difference between the predicted score and the ground truth score. And finally, the important one is loss, or which is also called top 1 loss, which means that what is the error made by each method in terms of choosing the actual best structure as the top structure. So here the loss will be able to tell us which one did better and which one did worse in terms of choosing the best structure. So this is how the performance of our method lociPARSE looks in terms of other state-of-the-art in terms of molecular level. So although there are too many numbers in the table, so you can concentrate that lociPARSE actually achieved 0.74 Pearson correlation score, which is almost twice than that of the second best performing method, ARIS. And this trend actually continues in terms of all the other correlation coefficients, no matter how you evaluated it. That is, did you do it in terms of globally or in terms of per target average? All the correlation coefficients of lociPARSE were actually much better than the other competing methods. Also, other important thing is the loss. So lociPARSE also achieved the lowest amount of loss, 0.07. That means that it can consistently rank the actual best structure as the top structure, even without the experimental ground truth. Although the performance of lociPARSE is not that good in terms of diff, but in terms of all other metrics, lociPARSE's performance is either competitive or better across the entire evaluation scenario. Now, this is the performance of lociPARSE in terms of molecular level. So what about the performance in terms of the nucleotide level, as I mentioned earlier? So interesting to note that the only other method that can do per nucleotide prediction is RNA-3D-CNN in the literature. There is no other method. So that's why you have compared with the only other method. And you can see that the per nucleotide level correlation coefficient is actually almost 4 times higher for our method than the other state-of-the-art method, RNA-3D-CNN. So that also says that not only lociPARSE can accurately predict the molecular level quality, it can also predict accurately the per nucleotide level quality as well consistently. And finally, to understand the impact of lociPARSE even more, we took part in the recently finished Cas16 challenge under the name of under the group name of Bhattacharya. And what we did is, for each of the given Cas16 RNA sequence, we have generated many deep learning based and non-deep learning based RNA-3D structures for that sequence, used lociPARSE to sample, pick the top 5 structures, and simply submit it to understand how lociPARSE actually works in terms of ranking capability. And this strategy alone actually has put us in terms of the top ranked groups, which is actually very difficult because there are some human groups also present there. So that makes the competition even tougher. So that means the ranking capability of lociPARSE actually again is showing that it can accurately rank even the Cas16 targets in terms of a blind assessment challenge. But the performance of lociPARSE could have been a little bit better. For example, I'll talk about that as a future direction. That during the development of lociPARSE, we did not take any kind of a stereochemistry violation into account. It's because the software that we used to calculate the LDDT's open structure, it didn't have that feature at that time. But OpenStructure recently has added this feature. So you can understand that whether a structure has a stereochemistry violation incorporated into the LDDT. So that can be one future direction. Also, will the architecture work in the similar way if we focus on other metrics such as DRMSD or interaction network fidelity inf? And finally, this approach can be extended in a similar way for other macromolecules, not only just RNA, but proteins, or most importantly, protein RNA complexes, perhaps. So in summary, lociPARSE was actually the first scoring method in the RNA literature to target LDDT as a ground truth instead of RMSD. And it can also accurately predict this per nucleotide assessment in a superposition-free way. The training code, data, and everything is publicly available in the GitHub link. And if you want to talk and discuss more about the architecture and perhaps the limitation and the future directions, I am presenting the poster, so feel free to stop by. And finally, I want to conclude this presentation by thanking the collaborators, funding sources, public data set by TR Rosetta RNA available, and most importantly, fellowship support given by the ICB and GLBC, for which helped me to come here, present my work here, and attend the conference in person. Thank you. Thanks a lot for listening.
Do we have any questions? Yeah, come to the mic, please, if you have a question.
Thank you for the presentation. I have a question. Since there are many quality assessment algorithms like yours, are separate from the predictors, but AlphaFold can do prediction and assessment at the same time. Even though there are many QA methods, they perform better than AlphaFold. So is there a space for QA method to play an important role in this whole assessment and pick model process? Because a separate model may spend more time to generate features and make prediction, but AlphaFold can do it at once. So is there any space left? Thank you.
I get it. So you're saying that if AlphaFold or maybe many other structured predictions, when they do the predictions, they can also give the quality assessment score. So what's the reason for a separate QA method, something like that, right? So yeah, so thing is, AlphaFold's predictions are only for the predictions that they are actually making, right? So during the prediction of AlphaFold structures, they will give the assessment scores. But what about you have RNA 3D structures, which is not predicted by AlphaFold. You have got it from a separate RNA 3D structure predictor. For that structure, AlphaFold will not be able to give you the assessment score. So that's why you need a separate QA method, which is dedicatedly actually. Yeah. You need a separate QA method which can actually take a 3D structure as input and can give you the assessment score. Because AlphaFold cannot take a structure as input. It can only take a sequence, predict the structures for you, and only give the assessment score for that structure.
Yeah, you are right. That point is right. Or for a follow-up question, is AlphaFold leading a fashion, the predictor and the QA, these two processes are integrated as the same model?
For AlphaFold or many other structured predictors, they are now having this confidence module, which is actually integrated in the same thing. So the prediction and QA is in the same architecture. But these QA methods, these are completely separately trained in the sense that they can take structural features as input. So that's where there is one difference between AlphaFold or the other structured predictors and these kind of QA methods. So this QA method can be thought of as, as one simple component in the whole pipeline. So you can either use AlphaFold's confidence level predictions, or if you have structures from other sources, there is this kind of methods actually available to help.
All right, thank you.
Thank you.
Okay.